Hi all, welcome to video class number 6. In this session we are going to study about what is called as continuous time Fourier transform. In short, it is CTFT. Now from here onwards I will be using the short form CTFT. That means continuous time Fourier transform. Now before going into the details, you should know why this CTFT. What is the need of this CTFT? So far in the last sessions or last classes, we studied about continuous time Fourier series. Continuous time Fourier series is a way of representing periodic signals. Only periodic signals can be represented as a infinite Fourier series. But we know that apart from periodic signals, there are certain set of signals called as aperiodic, which are not periodic, obviously. A periodic signal is signal which will not repeat itself. So some of the examples are, say this is a pulse, this extends from minus t to plus t, and all other areas the signal is going to be 0. So that means this is a short duration sequence. It is not periodic because it is not repeating. So similar is the case with this type signal, this one. So all these comes under the category aperiodic signal. Now in order to represent these signals in the frequency domain, that is, just as in Fourier series gives you an idea about the frequency components of a periodic signal. Similarly, if you want to learn about the frequency components in a periodic signal, we need to have a similar type of representation. So such a type of representation is what is called as a continuous time Fourier transform or CTFT. Now we need to have an idea about, or there is a relationship existing between the periodic signal and the aperiodic signal. Say consider this as a periodic signal. So just consider these are equidistant. So this is t, that means the signal repeats at every t. So this is xp, call this as xp of t. Now, can you convert this into a periodic sequence? Of course. If you extend this t to infinity, if this t is extended to infinity, the signal looks like this. That means this is going to be a rectangular pulse which varies from 0 to t, right? It's not t1, 0 to t, right? So that means what can you say about the relationship between periodic signal and aperiodic signal? Any aperiodic signal is nothing but it is xp of t as t tends to infinity. As you extend that t, extending this t to infinity will make that signal aperiodic. So now, to represent a particular signal, x of t, say, into in continuous term Fourier transform, the x of t should possess certain conditions. Here also those conditions are called as Dirichlet's conditions, as we studied in the case of Fourier series. The number one is x of t. We know, we are not aware of, from this x of t can have values anywhere between minus infinity to plus infinity. Whatever may be the value, if you integrate that from minus infinity to plus infinity, that should give a finite value. That is, this x of t has to be integrable. That's the first condition. The second condition is x of t should have finite number of discontinuities. There in the case of periodic signal we say finite number of discontinuities within a period. Here we don't have to mention anything about the period because this is an aperiodic signal. So anyway, that signal will be, say for example, this signal will be having a discontinuity. Say look at this, at minus t this function switches to a high value and at plus t it switches down to the low value. So that means there is a finite number of discontinuities. Now the third point is x of t should have a maximum, finite maxima and minima. In this signal again you have one maxima and one minima throughout that signal. So this signal can have continuous time Fourier transform. So this is a very important question that can be asked. Sometimes question can be asked, a signal will be given and you will be asked for whether that signal is having CTFT or not, or you should speak something about the existence of CTFT. Now, consider an aperiodic signal x of t. Now you want to have this, this is actually a transform. Just as we studied in Laplace transform, that transforms a time domain signal to frequency domain, this is also a transform. And that transforms a signal in time domain to a frequency domain. And that is represented by, or that is designated as x of omega. Let's call this as, I will be following this notation. X of omega is equal to. Now how this is formed? See, take your x of t, multiply that e raised to minus j omega t, just as we studied in Laplace transform. In Laplace transform, just for a recap, that is, it is multiplied by e raised to minus st. Instead of that, we multiply the signal by e raised to minus j omega t, and you are integrating through from minus infinity to plus infinity with respect to time. This is your x of omega. And this omega is a continuous variable. That means this function is a continuous variable. Okay. Now, this x of omega is so in some textbook that may be represented as x of j omega, or it is x of e raised to j omega, or it is x of f. All these represents the same thing, that is CTFT. I told you that this is a transform. So a signal can be, a time domain signal can be transformed to frequency domain x of omega, x of t. When you apply Fourier transform, that will get converted to x of omega. Now, since it is a transform, there is also an inverse relationship. If you have the x of omega, you will be able to get x of t, and we call that as the inverse continuous time Fourier transform. And this is the equation for the inverse Fourier transform. X of t is given by, now look at this, there is a slight difference. Now in this case, x of t is multiplied by e raised to minus j omega t. Here x of omega is multiplied by e raised to plus j omega t, and you are integrating from minus infinity to plus infinity with respect to omega. Here you are integrating with respect to time, since it is a function of time. You are integrating a frequency domain, omega dependent function, hence the integration has to be with respect to omega, and the difference is it has to be divided by 2 pi. So this is the inverse Fourier transform. Now something about your x of omega again. Now this, when you consider this x of omega is the frequency domain representation of an aperiodic sequence. Generally we dedicate this for representing the frequency domain representation of an aperiodic signal. Now just have a comparison of the frequency domain representation of a periodic signal and the periodic signal. In periodic signal, we represent that by Fourier series, which we have found out that to be discrete, while the frequency domain representation of a periodic signal is continuous in nature. That's a major difference that you need to note and remember. Now let's have some more about this x of omega. I have already mentioned that x of omega is a continuous function. Okay. Now when you consider a periodic signal, you know that in Fourier series representation you will be able to find out Cn. Once Cn is known, you can draw the Cn versus n, right? So if you try to draw Cn versus n, we have already studied this with n, you will be getting a graph similar to this, right? Yes. Now, what is the spacing of these spectral lines? These are called as the spectral lines. Different frequencies will be holding different amplitude, but they will be discrete in nature. Now, let me tell you about the spacing. What is the spacing of this? How will you find out the spacing? You will find out the spacing from the value of Cn or Ck. that is used in. So this is actually, these are the expressions of Fourier series. Now when xp of t, that's why I use xp of t, referring to periodic signal, and the corresponding exponential Fourier series coefficient is ck. It is given by 1 by t integral 0 to t x of t raised to minus j k 2 pi by t into t. Now when you add this, when you substitute the values for k, so k can vary from minus infinity to plus infinity, only the all numbers, that is 0, 1, 2, 3, etc. No numbers in between. So that means, now when you substitute this k, you can see that the spacing will be always 2 pi by t, right? So from this expression, this is 1 2 pi by t when k is equal to 1, when k is equal to 2, it is 2 pi by 2. So every time the spacing will be 2 pi by t. So at every 2 pi by t, there will be a spectrum. That is what we can see in a Fourier series representation. Now we know that from this study, we have found out that this x of t is nothing but xp of t as t tends to infinity. When you extend your period to infinity, you can convert any signal into a periodic using that. In this spacing, what will happen to the spacing when t tends to infinity? So the spacing is 2 pi by t, right? It is 2 pi by t. The spacing is 2 pi by t. So look at this. The spacing is 2 pi by t. What will happen as t tends to infinity? 2 pi by t tends to infinity. So this becomes 0, almost 0. That is, the spacing between each spectral component becomes equal to 0, right? That means when the spacing becomes equal, when the spectral lines become more and more closer to each other, right? That means this is going to be a continuous signal. Now what happens when t tends to infinity? That becomes an aperiodic signal, and the spectral lines becomes a continuous spectra. That's why I told you x of omega is a continuous function. Hope you understood this. Now so that's all about the basics of Fourier transform. Now let's do some problems on Fourier transform. Okay, let's do some problems. Now the question is, find the Fourier transform of the following signals. I'm again reminding you that you should take down all these things in your notebook. You should do it by yourself. I'm just showing some of the problems, how to do the problems, how to work out, and you should do by yourself every steps. Now the following signals. Number 1, an impulse signal. An impulse signal. We know that what impulse signal is. That is, say x of t equals del of t. Now your x of omega, you are asked to find out x of omega. X of omega is integral minus infinity to plus infinity x of t e raised to minus j omega t dt, and this is integral minus infinity to plus infinity del of t e raised to minus j omega t dt. That is, we know that del of t exists only at t is equal to 0, right? So when t is equal to 0, that means this becomes equal to 1, right? So there is no, so this becomes integral minus infinity to plus infinity del of 0 or del of t dt. So this becomes equal to 1, and the answer is going to be equal to 1. Okay, so at t is equal to 0, del of t is equal to 0. So in that case, this exponential term gets vanished. That means it converges to the basic definition of an impulse signal. Now the second signal, you have e raised to minus at into u of t. E raised to minus at into u of t. How to do this problem? Using that same expression, the same expression, that is x of omega equals integral minus infinity to plus infinity e raised to minus at into u of t into e raised to minus j omega t dt. So this can be written as integral minus infinity to plus infinity. You can take this u of t as 1 and this reduces to, since it is u of t, the integral limit reduces to 0, or it extends from 0 to infinity because of u of t, and you can put this together, a into, okay, so this will be, you can take j, j outside, okay, so this will be e raised to minus omega plus j omega plus a into t, right? You can take minus and t outside, so you will get this as j omega plus a into t, that is integral dt. Now what is the integral of this? This is e raised to minus j omega plus a j omega plus a divided by a plus j omega over the integral from, or the upper limit, from 0 to infinity. Now when this is into t, okay, now what happens at t is equal to infinity? T is equal to infinity, this becomes 0. When you apply 0, this becomes 1. That is 1 by, so this minus of minus, so this becomes 1 by a plus j omega. Okay, now this is your x of omega, or this is called as a CTFT of e raised to minus at into u of t. Now you can have a plot of this. Plot is very important. I forgot to say about the plot of this. What is the plot of this x of omega of a impulse signal? That's going to be equal to 1, and it looks like this. This remains a constant. What's the meaning of this? This del of t consists of all the frequency with amplitude equal to 1. That's the meaning of this. Now, how to draw this? How to draw the spectrum of the signal? That is, we want to find out the frequency components of this. So you look at this, the signal x of omega is a continuous thing. That's what I told you, that CTFT or continuous time Fourier transform is continuous in nature. Now let's see what about this. This one is x of 1 by a plus j omega. That means this is a complex signal, or this can be written of the form a plus a c plus a real plus j imaginary form, right? Now how to do that? Or you can find out this amplitude of that. Okay, so anyway, we understand that the x of omega is complex in nature. Now if a quantity is complex, say c plus jd, right, c plus jd, then this complex number has got, you can represent that in the magnitude angle form or polar form, that is magnitude angle phase. Now what is your magnitude? Magnitude is root of c square plus d square angle tan inverse d by c. Okay, so similarly you can have the magnitude of x of omega, that is x of j omega or x of omega is given by 1 by, look at this, 1 divided by, what is the magnitude of this? This is a plus j omega, so the magnitude will be root of a square plus omega square, right? And what is the phase of this? This is angle of x of j omega. I told you that this is a imaginary nature. That means it will be having a magnitude as well as phase, and the phase is given by tan inverse. How to calculate the phase of this? The phase is, say for example, if you have C by D, the phase is calculated in this way, that is angle C minus angle D. So in this case, what is the angle? This is imaginary term is 0, that means phase is 0. Now here the imaginary term, you have imaginary term and real term, that means the phase is tan inverse omega A. Now this is equivalent to our C by D, so that is angle G of j omega, so x of j omega, angle x of j omega is equal to tan inverse minus tan inverse, so this will be 0. The phase of this part is 0, this part is tan inverse omega by A, so this will be 0 minus, so this is minus tan inverse omega by A. Now how will you plot this? Plot the spectrum of this. You can have a plot like this. Say you may find out by yourself the values of this. I will just explain how to find out this. Okay. Say draw the column like this. Omega is equal to 0, say some 0.5, 1, 2, then 5, some values. So these are all the arbitrary values for omega, and find out x of j omega, magnitude x of j omega, angle x of j omega. Okay, so that means how to find out magnitude of x of j omega? Substitute omega to be equal to 0. So what's going to be 1 by A? Okay, for this problem, take A is equal to 2. Take A is equal to 2. Okay. Now, if A is equal to 2, taking A is equal to 2, you can find out this. So, this will be 1 by root of 4. This is 0, right? So, this is 1 by 2, which is equal to 0.5. Now, similarly, you can find out for 0.5. 0.5 will be getting 0.485. Similarly, you may find the values for all those things. Okay. Now, in the same way, you can find out the angle. Say I'll just do some, 2 values for you. That is, say when this is omega by A. A is taken to be 2. So that means you can write like this, minus tan inverse omega by 2. Right. So A is equal to 2. When omega is equal to 0, this is tan inverse 0. See, tan inverse 0 is 0. So the answer is 0 here. Now what about minus tan inverse 0.5? That is 1 by 4. Tan inverse 0.5 by 2. That is 1 by 2 into 2, 1 by 4. So the answer is going to be minus 14 degree. Right. Now similarly, you can find out all these values for this. Okay. Now I will explain once again how to find the phase of this. Say, just listen please. If suppose you are getting x of j omega is of the form a plus jb divided by c plus jd, how to find out angle x of j omega? That is, I'm actually telling you how this expression is obtained. For those who don't understand, please listen here. So I think you will understand this. Now what is the phase of this numerator? This numerator phase is tan inverse b by a, and the denominator phase is tan inverse d by c. So what is the net phase? Net phase is the numerator phase minus the denominator phase, so that this will be tan inverse b by a minus tan inverse d by c. So in our case, the phase of the numerator is 0, while the phase of the denominator is tan inverse omega by a. So that's why you got this as to be 0 minus tan inverse omega by a. That is minus tan inverse omega by a. So you may calculate all these values for these values of omega, and you draw the graph of that. So finally you will be getting a graph of this form. You will be getting the magnitude spectrum in this way. You will be getting a magnitude spectrum in this shape. So this is your x of j omega versus omega, and you will be getting a phase something like this. Okay, so you may say this is 0, 1, 2, 3, etc. This is your omega. This one is omega. X of j omega is there. Then okay, you can take this as, say, some 30 divisions, my 30 degree. So this is your phase. Phase is expressed in degrees. So 30 degree, 60 degree, 90 degree, etc. So this will be minus 30, minus 60, and so on. Minus. So here is it. I think you haven't seen that. So this is how the phase plot looks like. You can plot this as 0, 30, 60, 0, minus 30, minus 60, and so on. So you may just have a try of this and find out the phase of this. So this is called as the amplitude spectrum of the signal, and this is the phase spectrum of the signal. So the questions may be asked in this way. So sometimes you may not be directly asked like this to find out the Fourier transform. You may be asked to find out the amplitude spectrum and phase spectrum of the signal. So the first of all, what you need to know is, when you are given a signal, first of all identify whether it is periodic or aperiodic. If it is periodic, you need to find out the Fourier series coefficient. If it is an aperiodic signal, you should go for this Fourier transform. And after taking the Fourier transform, you should find out the magnitude as well as the phase. Magnitude versus omega is what is called as the amplitude spectrum. Okay. Now the phase versus omega is what is called as phase spectrum. Okay. So hope you have understood all these things, and okay. Now so you may take down this as a homework. You don't have to do this in Google Classroom, just for a practice. Say, consider this: x of t is equal to e raised to minus modulus t. E raised to minus modulus t. Find. So you may take down the question. Find the Fourier find the amplitude and phase spectrum of x of t is equal to e raised to minus modulus t. Now, what is the shape of e raised to minus modulus t? E raised to minus modulus t will look like this. So this is the signal whose Fourier transform you need to find out, or rather the amplitude spectrum and the phase spectrum. Try to do it by yourself. Thank you very much. Okay. So in this section we have studied about continuous time Fourier transform, and we started with the basics of that, the conditions for a signal to have a Fourier transform, and we have seen the Fourier transform equation, and we have also seen that this Fourier transform is a continuous function. That's the major difference between the frequency domain representation of a periodic signal and an aperiodic signal. And not only that, we have also seen the inverse relationship. Okay, and some of the we have done some problems. We found out the Fourier transform of impulse signal and e raised to minus at into u of t. And the importance of this is finding out x of omega means, and x of omega can be a complex number. So it has got a magnitude and an angle form, as I have specified already. So now you can have the phase amplitude spectrum and the phase spectrum. So questions may be asked in this way: find out the amplitude spectrum and the phase spectrum of a signal. Now, moving further, let's see some of the standard signals, some of the amplitude and phase spectrum of a standard signal, and of more importance to us in this course as well as in your coming courses in various semesters. So Among that, one of the important signal is the rectangular signal. Now, rectangular signal, a periodic rectangular signal, say I'm going to draw this figure. Rectangular signal is of the form, it is having an amplitude 1 which varies from minus tau by 2 to plus tau by 2. So this is a rectangular signal. Now, and we know that this is an aperiodic signal. This can have a Fourier transform. It satisfies all the conditions, all the Dirichlet's conditions. So you can have x of omega. So in order to find out the amplitude and the phase spectrum, the first and the foremost thing is we need to find out this x of omega for this x of t. Okay. Now you can define this x of t as, what is x of t? X of t is equal to 1 for, this is t between minus tau by 2 to plus tau by 2, right? And it is equal to 0 otherwise. So that's why this is a periodic signal. And now this has got a frequency domain, and the frequency domain can be explained by this Fourier transform. Now let us see what is this x of omega. Just rewriting the basic expression, that is minus infinity to plus infinity, x of t e raised to minus j omega t dt. This is the basic expression. Using this expression, we are going to find out x of omega of this rectangular signal. So when I put it is equal to 1, it varies from minus tau by 2 to plus tau by 2. That is, this is minus tau by 2, this is plus tau by 2 into e raised to minus j omega t dt, right? Now, and you are integrating this, the result is going to be e raised to minus j omega t divided by minus j omega being the constant, that has to be multiplied, minus j omega varies from minus tau by 2 to plus tau by 2, right? So you will be getting an expression like this, 1 by j omega into, okay, e raised to, so putting e raised to minus, instead of t you put tau by 2, so this will be j omega tau by 2, okay, so you have a minus here, right? Minus, already you have a minus, then this minus of minus, so that becomes plus e raised to plus j omega, this is e raised to minus and minus tau by 2, and this minus gets, this becomes positive tau by 2, right? So now if you put 2 and 2 here, so if you multiply this by 2 into and 2j omega, what happens is you can bring this together. No, this is e raised to j omega tau by 2 minus e raised to minus j omega tau by 2 by 2j can be written as sine omega tau by 2. That means what I said is, you are taking this and combining this together, you can write as sine omega tau by 2 into 2 by omega, right? Now simply I am multiplying this by tau, by the variable tau and tau, right? Tau is nothing but it is the pulse width of, this is, and from this to this is minus tau by 2, from this to this is plus tau by 2. Now if you have this, this is the pulse width of this, so the pulse width is tau. Now I am simply multiplying and dividing that by tau, okay? Now you will get it, so that this becomes, this is of the form, so this becomes of the form. The objective of doing that is, we want to get sine theta by theta form, right? So this theta here is omega tau by 2. So the denominator needs to be omega tau by 2. So there is a lack of tau, that's why I put tau in the denominator and numerator. So combining these together, that is, so you can combine this, so you can bring this 2 down, so this becomes omega tau by 2 or omega tau by 2, that is the denominator is equal to just as sine theta by theta. If you have sine theta by theta, that function is called as, we have already learned in our basic course, that is called as a zing of theta. So you can represent this as tau into, that is the pulse width, into zing of what? Omega tau by 2, right? So okay, now we have derived this expression for x of omega. So this is going to be the Fourier transform of the signal. Now I'm going to have a plot of x of omega, plot of x of omega. Okay, so that's going to be your amplitude spectra. When you draw this amplitude, so x of omega, that's going to be your spectra. And let's see how this spectra looks like. Now this is, we know that this is tau into sine omega tau by 2. Now this becomes a function of, tau is a constant, tau is the pulse width, well so tau is a constant, so the only variable is omega. Now we are going to plot or to have a plot which varies with omega, and here you are going to draw x of j omega. Okay, now we know that, so this is the point that omega is equal to 0. Let's see what is the value of the signal. So x of omega, what is x of omega at omega is equal to 0, right? So this is sine of 0, or this can be written as sine omega tau by 2 to omega tau, right? Sine is nothing but, so you can tau into sine omega tau by 2 by omega tau by 2, right? This is what is being written as sine of t. So when omega becomes 0, this becomes, okay, this becomes sine 0 by 0, tau into sine 0 by 0. What is that? We have studied in limit theorem that as theta tends to 0, sine theta by theta is equal to 1. By L'Hospital's rule, you can differentiate this and differentiate it. Again, substituting theta to 0, you will get it as 1. So the answer is going to be tau. So that is going to be the maximum value. Now why I told that it is a maximum value? Now as omega varies, what happens is the denominator also increases. So as the denominator increases, that value is no longer going to be equal to tau, it will be less than tau. So that is your maximum value tau, right? Now what happens is, now on the either side omega increases, omega in the positive half and omega in the negative half, and that will be determined by this sine function. So it will have a sinusoidal way of variation, so you can draw in this way. So this will be symmetric on this along this imaginary axis. So now it will be having a sinusoidal pattern, but what happens after this, after omega increases, the amplitude also decreases because of this. Okay, now you won't get this much amplitude in the next in the next cycle. Again this will be again less than, so this amplitude will, this amplitude is greater than this amplitude, and it goes on like that. So you will decrease and so on, it will be going like this. So similarly in this part also you can draw like this. Okay, now So this is how you will get x of j omega, or this is what is called as, this is the magnitude of x of j omega of this versus omega. So this is x of j omega versus omega, and this graph is called as the amplitude spectrum. Amplitude spectrum. Okay, amplitude spectrum of this rectangular signal. Now look at this. This has no correlation. When you look at the figure of this, it seems to be entirely different, but the same signal or this signal is the Fourier transform of this rectangular signal. So in other words, this signal consists of frequencies of various amplitude as shown in this figure, and the combination of this yields this rectangular signal. Okay, now this is called as a frequency response, or we call as the spectrum, frequency spectrum of the signal. Now something more about this signal. When you analyze the signal, that is, you must understand that this is a rectangular signal in time domain. When you convert that, this is your CTFT, right? This is your CTFT. When you convert this, you can see that there are a lot of frequencies with different amplitudes. See, zero frequency, that is DC, and so all these are frequencies with different amplitudes. When they combine together, you're going to get the signal. Okay, now something about this signal. This has got some, as you see that it has a sinusoidal variation, and this crosses at zeros. This crosses at the real axis, or this omega axis, at the zero. So these are called as the zero crossing points. Now can you say which is the zero crossing point here? So say let omega be, what happens at omega is equal to 2 pi by tau. So substituting, say you can have this. So just again writing here for you, x of j omega is tau into sine omega tau by 2 by omega tau by 2. So this is what is called as a sinc function. So I'm just elaborating it once again. Now when you substitute omega to be 2 pi by tau, what happens? 2 pi by tau. So when omega is equal to 2 pi by tau, that is, say, I'm just doing it for you, sine, what happens to that? This is tau by omega tau by 2 into sine omega is, so here also you can substitute, for omega. I'm here just substituting some omega as 2 pi by tau into tau by 2. So this tau and tau cancelled, right? 2 and 2 cancelled. So that results in sine omega. What is sine omega? Sine pi is equal to 0, right? So now the sine pi is equal to 0. Now the sine, actually this function, that is this sinc function, starts from 0 at tau, and then it decreases, right? So then it will find its first crossing point at this point and this point, and we have found out that point to be 2 pi by tau. Why we call this as, because at 2 pi by tau this sine becomes equal to 0. That means you can say that at every 2 pi by tau, so this is 2 pi by tau, this is also 2 pi by tau, but what's the difference? This is minus 2 pi by tau, right? So omega is negative here omega is positive. So this will be this is 1 times 2 pi by tau, this is 2 times 2. So at every 2 pi by tau, this signal crossover, so it will be having a 0 crossing. So that's the first point that you need to do. So this one is you can see that you have this lobe. This is called as a main lobe, or the portion between minus 2 pi by tau and plus 2 pi by tau. That is, as omega varies from minus 2 pi by tau to plus 2 pi by tau, that is this space. This region we call as the main lobe, and all the x of j omega after 2 pi by tau and before minus 2 pi by tau are called as the side lobes. So these are the side lobes. Okay, hope you understood this. So these are called as the side lobes and main lobes. And as you can see that the amplitude of this decreases as omega increases on either side. Okay. Now now one more thing is with regard to the main lobe, what happens to the main lobe as tau increases? What is tau? Tau is the pulse width, right? Now as the pulse width is made longer, what happens? What happens to the main lobe? Main lobe becomes 2 pi by tau. That is the pulse width as, so this is 2 pi by tau, no? As tau increases, what will happen to this width? This is the rectangular pulse width is tau, and tau increases means 2 pi by tau decreases. That means this main lobe gets shrink like this. So as 2 pi by tau decreases, you will be having a, say, something like this. So this gets shrinked. So the main lobe gets short. Main lobe gets narrower and narrower as tau increases. So there is also such a relationship as well. Now going into this, so this is called as the amplitude spectrum. Okay, we studied about the Fourier transform of a rectangular signal. So you found out that to be a Ising signal. Now next one is a phase spectrum. Now when you look at the phase spectrum, now that is angle x of j omega, which is equal to 0. Angle x of omega is equal to 0 when zinc of this function greater than 0. That is, I've just drawn it exactly underneath this spectrum just to show this region, that is a space between minus 2 pi by tau and plus 2 pi by tau. X of this zinc function is positive, is greater than 0. So over that region the phase will be equal to 0, and it can be plus or minus pi whenever the zinc function is less than 0. That is, zinc function can be less than in this region as well as in this region. What is the difference? In this region you have the positive omega, in this region you have the negative omega. So during the negative omega you will be having plus pi phase, and during the positive omega you have plus. Now look, during this region you have 0 phase, and over this region you have again minus pi. The reason is this is omega is positive here. Now in this case omega, whenever the omega is negative, then the phase is plus pi. So this is actually the phase spectrum of this signal. Now one more question is there, one more standard signals is there, that is a triangular signal. Okay, so now this triangular signal is given by x of t is equal to 1 minus 2 modulus tau by tau for t less than tau. This is how it is drawn. It extends from minus tau by 2 to tau. Now you can use this expression to find out x of omega, and the difference is here, since these two functions are over this interval minus tau by 2 to 0, this is an increasing function. Over 0 to t by tau by 2, this is a decreasing function. Therefore this integration has to be split, so that integration from minus tau by 2 to 0 and 0 to tau by 2, resulting in, and finally what you are going to get is, you are going to get your x of omega as x of omega as tau by 2 into zinc square omega tau by 4. Now what is the zinc square? You know, this is zinc of t. This is actually the Fourier transform of, this is actually zinc square of t. So this is zinc of t. Now when you take the square of this, it will be same as this, but what about the negative half? Negative half becomes positive. This is going to be the shape. Okay, now you may derive by yourself. You must find out this by yourself, do this integration and arrive at this result. And for your information, it is already solved in your textbook. You can refer Ramesh Babu, Signals and Systems by Ramesh Babu for having this, for having the derivation of this, and you may draw this x of omega, arrive at this expression. So this is your spectrum of the signal.